Sitting behind me is our Sdsl phase change heat transfer test facility. This is the oldest test facility in our lab, and its objective is to perform fundamental studies on condensation, heat transfer, and pressure drop in horizontal channels. We've studied horizontal channels ranging from the micro scale all the way to the macro scale, and we experimentally measured the heat transfer coefficient and frictional pressure gradient as a function of the vapor quality, or the mass fraction of vapor, the mass flux, which is the mass flow rate per cross-sectional area, and as a function of fluid properties, which corresponds for a pure fluid to saturation temperature or reduced pressure. So as I've said, we've performed many of these condensation studies on a wide variety of single component fluids. This would include synthetic refrigerants that you would find in typical air conditioners in residential applications. We've also studied condensation on hydrocarbons such as propane and ethane, which is relevant for the chemical processing industry. And we've studied condensation, some of the more natural refrigerants that are getting some attention these days, such as carbon dioxide and ammonia. In addition to single component fluids, we've studied condensation on multi-component fluids, which would be mixtures of hydrocarbons and refrigerants, or mixtures of different refrigerants, or mixtures of hydrocarbons such as propane and ethane. So besides just measuring these quantities and looking at the experimental trends, we try to understand why these trends happen in the first place. In addition to that, since condensation involves the flow of liquid and vapor simultaneously, there could be many different complicated effects that are happening, such as what the flow looks like at a given point in the condenser. To do that, we perform what's called flow visualization experiments, where we take high-speed video of the condensation occurring in a transparent test section. So what you're looking at now is an image of several different videos taken at several different points in a typical condenser. Starting with the annular flow, you have a large quantity of vapor where barely any fluid has condensed, where you have very high vapor velocity and very thin liquid films. Moving on, you have sort of a wavy regime where you now have some condensate accumulating at the bottom of the tube. That's basically gravity doing the work, causing the pool to accumulate. And then moving on, you have intermittent flow where there is very little vapor, so it kind of forms a train of bubbles that go through the condenser. And finally, you get even more bubbly flow until you're fully condensed. So with these videos, we understand basically what the flow is looking like. So the smaller you go, you may have different effects of surface tension or gravitational forces, which can affect your flow regime transitions. In addition to that, we also look at image analysis or image processing, where we can try to quantitatively measure things like void fraction or upper film thickness or pool thickness for the case of stratified flow, to try to develop more sophisticated physics-based models. So when we put all of this together, our experimental measurements of the heat transfer coefficient and pressure gradient, coupled with our flow visualization experiments, we come up with what we call flow mechanism based models. So basically, we take a look at like existing correlations for heat transfer or pressure drop, and we replace them with stuff that's governed by the fundamental physics of flow, and we develop these new correlations or new models, and we can see that the agreement matches much better. So we do this all the way for microchannels, all the way to macro channels, and we see very strong agreement.